Okay, now we're going to look at another application of the derivative and how it can tell us information about the graph of a function. What a derivative tells us about a function graph. What a derivative tells us about a function graph. Okay, so this is pretty cool. We can get some more precise information about the behavior of the actual curve of a graph using the derivative. And so we're going to start with a basic sort of diagram here of a function. Maybe we'll call this function f, this part of the function f. And so first thing I want to do is remind you that the first derivative describes the slope of the tangent line. And so I'm just going to go through and draw a few tangent lines on this curve of the function f, and then we can kind of talk about the observations that we've made here. So let's look at the tangent line right there. Let's look at the tangent line there. Let's look at it here, 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 and one more there. Okay? And so what we start to observe is that all of the tangent lines to the left of the peak, they're all slanted in a positive slope direction. Because the slopes of the lines on the left side of this graph are positive slopes, f prime, so over here on this left half, f prime of x is positive. The derivative of this particular function has a positive value on the left side of this graph. And furthermore, once we cross this middle point, all of the slopes are now negative slopes. They're all pointing downward. So on this side of the graph, we see that f prime of x is negative. Okay? And so this sort of indicates certain behavior about the function f, that blue curve that I drew initially. And so this is what the first derivative tells us. Let me see if I have a better blue marker here that we can use. So we'll label this first derivative. We'll see what the first derivative tells us. So the first derivative tells us, well, if f prime of x is greater than 0 for all x in some interval, I'll call it capital I, you might want to label that as some interval. If the derivative is positive for all the x values in an interval, so you can't have it positive just at a single x value. But if the derivative is positive for all x's in an interval, then f, the original function, like we have over here, on the left side, let's give this graph an x-axis and call this value c. We could say f prime of x is greater than 0 for all the x values less than c. And since that's an entire interval, we see that this implies that the f graph has to be going up if our tangent line slopes are positive. And so if the function is going up, that's called increasing. So what we say is, whenever f prime of x, the first derivative, is positive, then the original function is increasing on that interval. Okay? It's going up from left to right. And similarly, we can say that if the derivative, the first derivative, is negative, less than 0, for all x in some interval. So if the first derivative is negative for all the x values in an interval, then f is decreasing on that interval. Okay? So the first derivative tells us increasing and decreasing behavior of a function. All right? And it's really nice when the function is continuous because you know you don't have any breaks or gaps in the function. All right? Now, furthermore, we have an even more interesting observation, you notice here that this particular function changes from increasing to decreasing. We had a positive derivative value over here, and we had a negative derivative value over here. And that change occurred at this high point on the graph. So if your function f is continuous at this point, at this value c, and the derivative changes sign, as it does here, it goes from positive to negative, then the point at c is going to be a local minimum or maximum. In the case where you're going from a positive slope to a negative slope, you're going to have a maximum. In the case where you go from a negative slope to a positive slope, you're going to have a minimum. Okay? So let's state that more formally. If f is continuous at c, that's important, it has to be continuous, meaning both sides of the graph have to meet at c, the limit has to exist from both sides, and the actual output at c has to be here, it can't be some other random place. So if f is continuous at c and f prime, the derivative, changes sign, goes from positive to negative or negative to positive at c, then what did we say? What does that tell us? Like this point here at c is a local maximum. So here, f has a local max or min, at c. All right, so the first derivative can tell us two things. It can tell us increasing, decreasing behavior, but it can also tell us local max and min points. All right? So that's what the first derivative is good for. Pretty easy to see that because the first derivative just represents the slope of the tangent line. Okay, just making sure we're still recording. My phone's been giving me trouble lately. Now let's look at the second derivative. A little bit harder to understand, but we'll do our best, right? So let's draw another curve or another function over here. And we'll say that it does this kind of thing just for emphasis of what's happening here. So this is the graph of f, and we're considering f double prime. Now one thing's clear, this function's continuous, and the tangent line slopes are positive all the way through. So this function is strictly increasing. It never has a zero tangent slope or a negative tangent slope. So it's increasing the whole time. But that's not what the second derivative tells us. The second derivative is the rate of change of the first derivative. And the first derivative represents the slopes of the tangent lines. So if we look at the slopes of the tangent lines again for this guy, we can see that at this point we've got just a slight slope, a very small slope, a small positive number. But as I move to the right, the slope of my tangent lines is getting steeper. They're getting bigger values. So my tangent line slopes are increasing until I get to maybe like right here where I reach my maximum slope. And then I'll switch colors here. And then from that point, after I reach my maximum slope, my slopes start to shrink again. They start getting smaller again. So what this means is my first derivative values are increasing, right? Because the slopes are increasing, which means that the rate of change of my first derivative is positive. Because my first derivative is increasing, the slopes are increasing, my rate of change of my first derivative is positive, which is the same thing as saying f double prime of x is positive. Okay? f double prime of x is positive for these red tangent lines. Now on the second half, my tangent line slopes reach this maximum value. Let's use a different color there. Let's use purple for where it reaches that maximum value. Okay? And then after that, with all the green slopes, my tangent line slopes are decreasing. So my f prime value is decreasing, meaning that f double prime is negative. Okay? All right, so what is this telling us? How can we describe this with the way the curve looks? Now, the curve looks, just to remind you, it's kind of hidden in there. It looks something like that. So what's happening is we've got this special point right here where we reached our maximum tangent slope, okay? But before that, my slopes were increasing, and then after that, my slopes were decreasing. That's how we figured out the values of our second derivatives. So what this means is if the slopes of your tangent lines are increasing, or your f double prime of x is bigger than 0, then what you get is a curve that's flexed down. It's bent down, right? If you imagine a sheet of paper here, this piece of paper is not bent. Now it is. It's flexed like that. And this is what we say maybe holds water. If it were to rain on this, it would kind of catch the water. Whereas if it were bent the other way, the water would run right off the surface, okay? So when our curve is bent like this, when it opens upward, we call that concave up. It opens upward. The mouth opens upward for concave up. And f double prime being negative, what that means is now we flex our paper or our curve the other way, and it sheds water, and the mouth of it opens down. It's concave down. And so this second derivative tells us not whether our function is increasing or decreasing, right? We already said this function is increasing, but part of it's concave up and part of it's concave down. So the second derivative will tell us that concavity. It will tell us which way the curve is bent. Okay, so the second derivative tells us concavity. And we'll state more formally how that works. So here's how it goes. If f double prime of x is positive, again, we have to look on an interval. So for all x in an interval, so if your second derivative is positive on some interval, then f, the original function, not f double prime, not f prime, but f, the original function, the blue curve over there, is what we call concave up on that interval. Okay? So a positive second derivative on an interval means concave up. And if f double prime of x is negative on some interval, then the original function f is what we call concave down. Concave down on that interval. Okay? No big deal, we could see that over here. So second derivative will describe concavity, while first derivative will describe increasing or decreasing. Now, let's talk more importantly now about this point here. When you have a point where the function's continuous and the second derivative changes sign, right? We looked at what happens when the first derivative changes sign, but when the second derivative changes sign, what happens? Well, this is precisely where the curve changes concavity. It went from concave up to concave down. Okay? So this point is not a local maximum or minimum, but it's what we call, it's a change in the way the curve is bent. All right? It's called an inflection point. We have an inflection here in the curve. We have an inflection point. Okay? So now, the second derivative tells us concavity, but it also tells us any inflection points. Okay? So how does it do that? Well, just like local mins and maxes for the first derivative, if f is continuous at c and f double prime changes sign at c, so it's a point of continuity and the concavity changes, then then f, sorry about that, f has an inflection point, at C. So that's what an inflection point is. It's where the concavity changes at a point of continuity. All right? So that's first derivative and second derivative. You know both of those of a function. You can use that information to help you graph the function more precisely in addition to what you know about plotting points. Okay? So now we know things like continuity, differentiability, increasing, decreasing, local min, local max, concavity, and inflection points, all to help us graph. You could throw in intercepts, x and y intercepts, domain, all kinds of stuff. Let's put all of this together with a concrete example here. So let's suppose f of x equals 2x to the third minus 9x squared plus 12x minus 3. Okay? And before we get too far into it, let's go ahead and point out that since this is a polynomial, it is continuous on its domain, which is all real numbers. So we don't have to worry about this guy not being continuous. This guy's continuous everywhere. It's the best scenario maybe we could hope for, or one of the best. So suppose we have this function. We're going to identify multiple things here. Identify intervals of increase and decrease. Identify local min and max values. Right, those go together. Use the first derivative to find both of those. Then let's identify intervals of concavity. And last, let's identify inflection points. All right, so we're going to break this into two components. We're going to start by looking at everything we can get from the first derivative, just to practice the concepts we looked at. Okay? So the first derivative, is f prime of x equals 6x squared minus 18x plus 12. And if I want to know where the first derivative is positive and negative, because of the intermediate value theorem with this nice continuous function, it would be a good idea to figure out where the first derivative equals 0, because if any other place where it doesn't equal 0, it's going to be positive or negative. So since we know we're going to be setting this equal to 0, just like when we find critical numbers, we're going to, because it's a polynomial, we're going to go ahead and factor it so we can easily identify where it equals 0. So I just pulled the 6 out and then factor the remaining trinomial. Okay? So now we're going to get if this were equal to 0, so the critical numbers here, for this to equal 0, x would have to be 1 or 2. Okay? And This derivative exists everywhere, so there are no critical numbers where the derivative doesn't exist. You also typically investigate that. So I've got our critical numbers here. Now what we have to do is this practice of, could be called many things, a number line chart, a sign chart. You've probably done this in an algebra or pre-calculus class. I put a lot of thought into how I'll set it up here, just because this video will be out there for a while. So what I'm going to do is I'm going to take and cut my number line at my critical numbers, 1 and 2. So I'm actually going to create a number line that's a band like this. That's my number line. And I'm going to squeeze 1 in there and 2 in there. I'm going to space those out a little bit. I'm cutting my number line at those values. And I'm making sure that they're in order. 1 comes before 2. Now, I'm actually going to create a table that has 3 rows. Okay? So I'm going to have a row for f prime, and I'm going to have a row for f. So I'm making those plenty big, so I've got plenty of room here to write. And then I'm actually going to cut my number line at my 1. So I'm going to create a column under my 1 and a column under my 2. And this is just going to help me organize my information. So this top row are my x values, my x number line. And the numbers that are here are all the x values less than 1. You don't have to write that, but just to be complete here, I'll write x is less than 1. This is where x equals 1. This is where x is between 1 and 2. And then here is where x is bigger than 2. You're welcome to leave those blank if you like, because it's sort of implied which values live in those regions. All right, so here we go. We're gonna track what f prime is on each of these, in each of these cells, right? And the place I like to start is at my critical numbers 1 and 2. So if x, right, these are my x values, you could even write x equals 1 here if you like. Maybe that's even better, right? If we're going to label everything, this will be x equals 1, and this will be x equals 2. So now, if x is 1, we already know that f prime was 0. That's where this number came from, and the same thing when x is 2. Now, because of the intermediate value theorem, and the fact that this polynomial f prime is continuous, we know that these are the only zeros, so that means before 0, every output of my derivative is going to be positive or negative. Okay? Same thing between 1 and 2, and same thing bigger than 2. Okay? So if x is less than 1, what I'm going to do is I'm going to use this factored version of my f prime function, my derivative, and I'll think of numbers less than 1 to substitute in for x. So if I plug any number less than 1 in for this x, and I subtract 1, I'll get a negative number. A number less than 1 minus 2 is also a negative number. So f prime is going to be 6 times a negative, which is positive. Okay? Then doing the same thing here, picking a number between 1 and 2. A number bigger than 1 is going to make this positive now, but a number less than 2 is going to make this negative. So I've got 6 times a positive times a negative, which is a negative. And last, if I pick a number bigger than 2, that's going to make both of these positive. 6 times a positive is a positive. So now we've sort of tracked where f prime is positive and negative. That's going to be super useful because we know what that tells us about f, right? We already discussed what f prime tells us about f. In fact, let's keep the same color. If f prime is positive, what do we know about f? Well, it tells us that f is increasing. Okay? So if we start answering the first part of this question, identify intervals of increasing or decreasing, well, we could say that f is increasing on the interval where x is less than 1, so from negative infinity to 1. Okay? Now, here f prime is 0. That means we have a horizontal tangent line. We're not increasing or decreasing there. All right? Then between 1 and 2, f prime is negative, so we're decreasing. So we can say, right, if f prime is negative, f is decreasing. So we can say f is decreasing on the interval between 1 and 2, like this. Here we have another horizontal tangent line. F prime is positive, so we're increasing again. So f is increasing from negative infinity to 1 and on the interval for x values bigger than 2, so from 2 to infinity. And we've got all of the intervals of increase or decrease. Done. The next part is to identify local min or max values. Okay? So let me erase this. Identify local min and max values. So what's happening here is we have, at x equals 1, we have a point where the function's continuous because this function's continuous everywhere. And f changes from increasing to decreasing. That means it's going up, flattening out, and then coming back down. So this is definitely a local maximum. Okay? And then the same thing here, we're continuous at x equals 2. We're going from decreasing to increasing, so this is definitely going to be a local minimum. All right? Now the question says find local min and max values. So what I have to do is I have to find the y value for this x value. And the way to get the y value for this is to plug it back into the original function. Okay? So what we're going to do is we'll say local max value of, and we need to figure out that number. And over here we need a local min value of, and we need to figure out that number. Now, I could do these numbers in my head, but sometimes the numbers aren't easy to work with and the function is not so nice. So I'm going to show you how I would do this on my calculator, which is a TI-36X Pro. And that could speed this process up, especially if you have numerous numbers to plug into the same formula. So here we go. All right, let's get focused here. What I'm going to make use of mostly here is this variable button, which uses x first, and this store button, which lets me store values in for variables. Okay, so the first thing I want to do is I want to store 1 in for x, because that was the first critical number. So I'll hit 1, store x, and then I have to enter to make that happen. So now I've got 1 stored in for my x value. Okay? All right, maybe my camera will calm down and just zoom on the calculator here. Now what I need to do is I need to type the formula for my function. So the formula is 2x, I'm using my x button, to the power of 3 minus, let me go back, hit the right arrow, minus 9x squared plus 12x minus 3. So if I hit enter, what it's going to do is calculate the value of that function whenever x is 1. So I enter and I get 2. So I know I'm going to put a 2 for my y value whenever x is 1. Now all I have to do is store my other x value in for x. So I'll hit 2 because that's my other critical number. Store x, hit enter. Then I'm going to go up to my formula, use my up arrow to get to my formula, and I want to reuse it, so I'll hit enter, and it retypes it. Hit enter one more time, and it recalculates it with the new x value. So when I plug in 2, my output is 1. Okay, so now let's go fill those values in on the table. So I know that when I plugged in 1, I actually got 2. As my y value. And when I plugged in 2, I got 1 as my y value. So now I know my local max value and I know my local min value. Got those done. Good. I could even specify that I have a local max value of 2 at x equals 1 if I wanted to be even more descriptive. Okay, now let's move on to the second half of the problem and look at concavity and inflection points. To do that, we need to analyze the second derivative of the function. So the second derivative. Let me see if I have a better red marker here. I may not. All right, so f prime of x, just to recall f prime of x, there we go. 6x squared minus 18x plus 12. If I differentiate again, I get my second derivative, which is 12x minus 18. All right, 12x minus 18. And again, if I want to know where this guy's, the second derivative is positive and negative, it could certainly help if I know where it equals 0. So to do that, to help me out with that, I can factor this. So there, you don't have to factor it because it's linear, but it's not a bad habit to get into, leaving 2x minus 3, which means that x equals 3 halves is our critical number, okay? Then we do the exact same thing as we did before. We set up our number line chart with that critical value, that critical number, and we look at f double prime and how that relates to f. So again, I'm going to set up 3 rows. The first row is going to be my x values, and I need to cut my x number line only at 3 halves, okay? My second row now is going to be f double prime, and my last row is going to be f. Let's get some information here. Oh yes, and I meant to write x equals 3 halves. Which means that to the left we have x values less than 3 halves, and to the right we have x values bigger than 3 halves. All right? And we already know that whenever x equals 3 halves, f double prime is 0. Okay? And again, because of the intermediate value theorem with its basic polynomial, everything here is negative or positive, and everything here is negative or positive. If I pick a number smaller than 3 halves to put in here for x, and I multiply it by 2, that's going to give me a number smaller than 3. Something smaller than 3 minus 3 is negative. 6 times a negative is negative. So f double prime is negative. Similarly, if I pick a number bigger than 3 halves and multiply it by 2, I get a number bigger than 3. Minus 3 is positive. 6 times a positive is positive. And so now, if f double prime is negative on an interval, then I know that f is concave down. It opens downward. And if it's positive, if f double prime is positive on an interval, I know we're looking at concave up. Now, when this was the first derivative and we had 0, that meant we had a horizontal tangent line. When f double prime is 0, we don't really know much about the function other than it's not concave up or concave down. It's not very useful to us, okay? So don't make any assumptions about what happens here. But we do know that this function, we can go ahead and state our intervals of concavity. Let me not get ahead of myself. We can say f is concave down. I'll abbreviate as CD. F is concave down on the interval from negative infinity to 3 halves. And similarly, f is concave up on the interval from 3 halves to infinity. So we've got our intervals of concavity done. And the last thing we need are the inflection points. So if you remember what we're looking for in inflection points, we're looking for f double prime to change sign at a point where the function is continuous. And this function, this f function we already said is continuous everywhere, so it's certainly continuous at 3 halves. And we go from being concave down to concave up. The concavity changes. The way the curve bends changes. So we definitely have an inflection point here. Now an inflection point is an ordered pair, right? So I need an x and a y. Well, the x is 3 halves, and then I just need my y. Well, my y, again, is calculated by plugging 3 halves, my x value, into the original function. And luckily, I've already stored that function in my calculator. So all I need to do now, let's resume where we left off before. I need to start by storing my new x value. So I'm going to type 3 halves, 3 divided by 2, and I'll hit store in for x. So that's my new x value. Then I'll go up to my formula, my function, and hit enter to retype it. And then I'll hit enter one more time to recalculate it with the new x value. And my y value, the output, is 3/2 also in this case. So that means that the inflection point is the ordered pair 3/2, 3/2. And so now we've accomplished all 4 tasks for this particular function. We've gotten used to how to use the first derivative, the second derivative, and how to set up these charts to help us identify all of the pieces of the function.